Okay, let's go ahead and get started. Thanks everyone for joining. Looks like we've got a good turnout. This is an Exceed webinar on Comet 101, accessing and running jobs on Comet. Mary Thomas will be our presenter. She's a computational data scientist and the lead for SDSC's HPC training. So she's got a lot of good experience that she's going to share with us today. First, I want to at least let everybody know about the code of conduct. Exceed has an external code of conduct that I assume everyone generally will adhere to. So thanks very much for your good behavior. And with that, I'll stop sharing and hand it off to Mary.
Hi, folks. So I'll start sharing my screen. What I'm going to do is share the desktop for a little while as we look at examples. So I'm going to talk about running jobs on Comet, and this is a real low level in a sense, if you can call anything on HPC systems low level, but it's a practical guide. It's just how to get on and get things done and find things. So it's intended for an audience of new people or people who need to be reminded. And so it's coupled to a markdown file that I've got hosted on a repository, which is listed in the presentation. But if you go to this particular repository, then I'll post it also on the chat window. You can find this markdown file, which is 98% synchronized to the material in the PowerPoint presentation and 95% working fine. I've tried to retest and rerun everything yesterday for a couple of reasons, and I'll talk about that in a moment. But if you find that things aren't quite right, recognize that it might be you're using a different library, or you're in a different directory, or you're doing some different code, of course. But if you can't figure it out, then get in touch with us, either myself directly or the Exceed consulting staff. The idea is to have this up and supported with code that you can download and use on Comet. So we keep refining these. And there's been a lot of changes to my talk. I've given this a couple of times because they're big changes too. They upgraded the operating system on Comet to CentOS. And it's little subtle changes, but things are different. So your old code may not work, which would be another good reason to be going through this material. So I'll give you I don't think we have time to do an interactive version where I'm running a lot of examples for you, but I've tried my best to just capture things as I see them on the terminal. So a bit of an outline here, which also is the outline on this presentation. We just go over an overview of Comet and look at using modules to manage the environment. And that's changed a little bit, and I'll talk about that. And then how to compile and link for Intel, PGI, and GNU compilers, as well as GPU. We go over examples, some advice on how to run jobs on Comet, parallel and serial, and then some hands-on examples. I start out with some GPU code and just a hello world. For everything, there's hello world and some enumeration so you can tell what's on your system and matrix multiply. And then the same hello world for MPI, OpenMP, and a hybrid MPI, OpenMP. So as you go through, the idea behind this page is you can cut and paste a command, and it really should just work on the system. So if I were to bring in a terminal and make it bigger font, and then, of course, this is a live demo, but I'm connected to Comet, and I just look at what's in the Comet 101 directory. There's a directory called Share Apps Examples. There's a lot of material in there, including Singularity containers and working code. And then the HPC training group, we're building up our own repo that will be directly connected to presentations and webinars that we're facilitating and supporting. So for example, today I've got code in Comet 101 for CUDA hybrid, and you can see the contents of the directory. So the idea is you should be able to cut and paste from the markdown file, and things should work, assuming copying and pasting works between your terminal application and where you're trying to work in my markdown file. Okay, so with that, let's get started. I'll move to the PowerPoint presentation. Again, I'll get this posted in the chat window, or maybe Jeff can, but we'll get that posted before the session is over. I know a lot of people like me have an abundance of Zoom meetings, and so it's important to stay on target, stay on track. Okay, so I'll go to slide presentation. Of course, that's not what I want. That's not what I want you guys to see. There we go. Can you guys see the outline fine? Can everybody hear me fine?
Yeah, it looks good. Sounds
okay.
Good.
All right, so hopefully this works. So again, it's the same flow of material as is in that markdown file. So as you go through the PowerPoint presentation, you should be able to go directly to these different sections in the markdown file and make things work. Everything in this talk is in the code directory, which is on Comet, and will also eventually be in a repository. All right, so just getting started. Again, there's that webinar location. We have a GitHub repository for SDSC HPC training. There's a lot of repositories in there, and one of them is webinars, where we keep material associated with our presentations. And then there's the Comet user guide, which is useful. I will point out they've just moved to CentOS, so there's lots of things in the user guide that have changed from the old user guide that you're used to. So be sure to refer to it if things aren't working quite right. And then companion tutorial information. And just a caveat, you really need to be familiar with running Unix commands and using SSH and running notebooks these days. And just a future plan, next month we're doing a talk on running notebooks on Comet, which is the way things are done on our machines. So we're going to talk about that and how to run them more securely. And so there's a tutorial, there's a repository that's just called Basic Skills, and in it, it's overview of Linux and some commands and how to use SSH and some things like that, if we have time at the end. But that's github.com/sdsc-hpc-training/basic_skills. And you'll find, I hope you find those useful and give me feedback if they don't make sense to you. And so you have to have a Comet account, and to do that you can get one in one day if you go to the Comet user guide and look at trial accounts. Eventually it takes you over to the Exceed website, but you make a portal account, and then that user account is used for all the systems that you might be working on. And then if you want to see what other training events we've got, go to this training on the main website, and it'll show you what we've got planned. So to log on, just a reminder, you guys are sitting over on your laptops, and somehow through the cloudy internet, you're going to access login nodes. And once you get logged on, and we have several login nodes, so you might see your command line prompt change, and you'll see examples of that in my examples. You then go through a switch and you access the different nodes on the cluster. The nodes have cores on them and GPU cards, and they're very large. And so the name of Comet is comet.sdsc.edu, and in the connecting basic skills tutorial, you can see how to use that. On Mac, it's pretty easy. There's a built-in terminal, and SSH is installed, and it seems to work fine. On Windows, there's a new Windows 10 terminal app with SSH installed on it, and it's pretty good emulator for Unix. It's not Unix, but it's pretty good. It's got most of the commands you might need. And on older systems, you would try PuTTY or Cygwin. Those all worked fine as far as I know. So you're going to log into the host name, and in case you know about keys and passwords and things like that, and you get tired of typing your password in, you can set up a supported version of passwordless login where you have your password key pair on your local system, and you upload a public key to the remote machine, and then once you authenticate the uploading of that information onto Comet, for example, you don't have to type your password in again, because the two systems talk to each other and exchange public-private key information. And this is one of the best tutorials I've seen, so I recommend you look at that. Okay, so again, logging on, that's just a revisit to that. When you log on, you'll see the comment, welcome, and some kind of message, and it might tell you the last time that you logged in. It's helpful to make sure that the last time they think you logged in is when you logged in, not somebody hacking your account. In general, these SSH connections are pretty secure. And you'll notice right now I've logged into a host name called Comet-LN3. There's also Comet-LN2, those change. So the first thing you're going to want to do, if you want to follow my examples, you want to go ahead and get the Comet 101 example directory from Share Apps Examples HPC Training. And then you'll see that you're going to get a few preloaded codes. The contents, when I printed this out, is CUDA code, some notebook information, MPI, OpenMP, and I've added a couple more that will show up in later images, a hybrid example, and the Intel Math Kernel Library example. So just a little plug before we move on to running jobs on Comet. Our new machine Expanse, if you haven't heard about it, it's going to be a very big machine, and it's going to have 728 nodes and 52 GPU nodes, 12 petabytes of storage, and it's built for composable systems, cloud computing, and standard HPC computing on CPU GPUs. So we're pretty excited about it. We're building it out this year, so then we'll be doing an Expanse 101 in the fall. And again, Comet is designed for what we call the long tail of science. I'll talk about that in a moment. But those are people, there's a lot of us who don't need 10 million cores, but we need a few thousand. And so Comet is built to support those of you who have a lot of jobs to run that are, again, need a few thousand core. And we're perfect for that. Our schedulers are optimized for that. If you need hundreds of thousands of cores, you should go to a different system where the schedulers are optimized for that. All right, so overview of Comet. This is one of my favorite pictures, is something from the 70s called the Stone Supercomputer. It won the HPC wire equivalent of the cheapest cost per flop, 0, because everything was free, and they got 20 megaflops. And these guys were at Oak Ridge, and they just went around and gathered all the old computers they could find, connected them, and called it a supercomputer, SOUPER. That comes from an old story of this village where they were very poor and starving, and somebody was hungry, so he got a big bowl and a pot and put it on the fire and put a rock in it. And somebody said, "What are you making?" Because I'm making soup, but I don't have a lot for it. And somebody said, "Well, I have a potato." So they donated a potato. Another villager walks by, "Well, I've got some carrots." And of course, the story goes, more and more people kept dropping stuff in, and by the end of the day, they had an amazing soup. Okay, so Comet, long tail of science. If you're ever allowed to travel again and you are near SDSC, come and walk through the machine room. We do tours all the time. It's pretty impressive. This is just a picture of the racks with the different nodes in them. So these are racks, in case you don't know the terminology. These little horizontal boxes are called nodes, and inside of them are all the cards that have these cores that you'll compute on. And if you walk in between, the racks are set up in 2 rows. It's really like a tornado in there. The windstorm is pretty hot and pretty amazing. So anyway, Comet is built for this long tail. So they did some research in evaluating and designing the system, and realized that a majority of computational work is done at what they call a modest or small scale. And let's build a machine then. They decided to build a machine that supports all of these people who, like I said, just need a few thousand cores as opposed to hundreds. And you can get, most jobs run less than 48 hours, but we can extend that. But they tend to be computationally and now data intensive. So the next version of Comet will have more cores, more GPUs, 282 GPU nodes. And be built for data movement and management, so we can support machine learning and a lot of the data science initiatives. It's funded by NSF. Some key statistics, 2.76 petaflops. Dell's our primary integrator, 46,000 plus cores, 72 GPU nodes, two kinds of nodes. And I just want to point out very quickly, to use Comet, you need to get an allocation. There's many kinds. I won't go through that in detail, but you can get an allocation because you've applied for something based on your science. You can get what's called a startup allocation. Those usually last for 1 to 3 years, and they're small amounts of CPU, but it gives you time to test and migrate your code to HPC systems. And then we have some large memory nodes, and there'll be more large memory nodes on Expanse. The network is a flat tree topology, in case you're interested in how networks work. It's InfiniBand. We have 7.6 petabytes at the moment of luster, and it may be more. These numbers change. Durable storage, 6 petabytes. You have a home directory, and you want to be careful about that home directory. It's got limited storage, and you really shouldn't run any code from it. You should put it over in a working directory. I'll talk about that briefly. Again, there's the layout of the machine. You can see how the wind is blowing behind these. We're outside the racks. You know, the node front is here, and it's blowing cooling air with the fans into the middle of them. So 72 nodes per rack, so that's 1,700 core. And then we have 23 racks, I think. 27 single rack computers. This is our network. It's your standard complicated HPC network. Everything from Ethernet to InfiniBand and storage, high performance, low archival, multiple switches. Those are, you can imagine the switching is complicated. And these are the compute nodes, Haswells and GPU and large memory, interconnected with some InfiniBand interconnection network, and then gateway hosting hardware and logging in, and then the cloud. We use internet too as well. So, okay, so for where do you store your data? We have several options. One is the Lustre file system. It's good for scalable large block I/O. You're going to have a problem if you're working with a lot of teeny tiny files and you have to move them. It's not optimized for that, and probably you'll get a note saying, hey, you're using up all of our bandwidth on the network with your tiny files. So think about the kind of files you need to move around and where they need to be. So you would go to Oasis Scratch Comet and store data there, and you have Oasis Projects NSF. You're allowed to use both of these, but they're not backed up. They're not, the Scratch is not backed up. We have SSD file systems. That's the /scratch. That's local to each of the nodes. Again, that's going to be there while you own the node and disappear when your job ends. So make sure you think about, if you want high-speed I/O during the computational cycle, that you then move your data off that node when you're done, before you lose your ownership of that node. And then you have your home directory, which is small and limited, and you can always find it by this $user variable. It's part of your environment variable. And again, it's not good at all for large scale I/O, and they really don't want you running your code from there. So this is a table version of the file systems. You can find all this information, and I have several tables in my presentation that are directly from the user guide. So you can go find that in the user guide and get more information. But on home, you only have 100 gigabytes. That used to be a lot, it's not anymore. And then these are the limits for the other file systems that you have access to. All right, so one of the newest things, if you haven't worked on a system like Comet, is using modules. They're becoming more common, but the modules are designed to help you more easily access the software environment that you need to use. If you need lots of different libraries, can you imagine having to install Amber and Gaines and other bioinformatics tools in your local directory and learn how to do all that sysadmin stuff? Well, you don't need to. The systems people install all the software and then create these modules that will give you, load in the right paths to the commands that you need. And I'll show you examples of that. So modules are very helpful. They just take a little bit of getting used to. And the caveat is be really aware of what's your current module environment, because you may unintentionally load in two environments that collide with each other, then nothing works. So you can purge everything and start over and reload the library paths that you need, and then things should work fine. And if they don't, contact the Exceed Consulting people. They're very, very responsible, 7/24 service, and very helpful. And very patient. So when I logged into a machine and I wanted to see my currently loaded files, I used a command called module li, short for list. I have a table of the commands. And it showed me I've got the Intel 2018.1.163 and an MVA pitch version. On whatever day, I might be getting a different one when I log in for the default environment. But if I needed to always use that version of Intel, then I would load that module in, so all my code continued to work. So you can customize your environment by using the right modules. To list the available modules, it's AV for available or avail. And this is huge. It's hundreds of lines long. And so I just chopped it to show you some module files for MPI Intel and some applications for Intel, but this is all cut and snipped down quite a bit. But you can, I often will run the commands, save all the information in a temporary file, then go in there and find what I need. It's sometimes tricky, but you can also go to the directory /opt/mod files. You're allowed to look in there. You can't write and change it, but you can browse through there to see if the library you need is there. If you can't find it, email consulting. So popular commands: list, available, display information, show information about a module. These are the same. Unload a module. Let's say you loaded the wrong Intel compiler in. You unload the bad one, the one the one you don't need, and load in a module that you do need with the module load command, or you can swap environments. I'll show you an example of writing your own module building script, which I find convenient. Then I make a script for doing a particular application, and I don't have to remember, and I can put those commands into my batch script if I want. So again, I logged on to Comet. I'm on login node 3, and my currently loaded files were by default these 3. Actually, GNU Tools doesn't show up anymore. That's a change from going to the new CentOS. Both Singularity and GNU Tools are in your path by default. And here's another listing of what's available for, we have LAPACK, MATLAB, Spark. So I looked at the modules available. And then you want to know how to understand this command called environment. It tells you this is just everything that you need to know about what variables are currently populated in my environment and how can I use them. Like the variable host name tells you what host name you're on. And this is, for me, a couple hundred lines long. So I just cut out and kept ones I thought would be interesting. There's my Python path. There's home. There's my SSH client connection. So I'm including I have an include path, so you can get all kinds of variables set in there. And the environment will change depending on the modules you've loaded, and what you've got in your .bash underscore profile or whatever shell that you're using and you're launching. So once you've loaded them, you can check and see, what do I have? So my current list of modules are these two default, and I'm going to add Spark. And then I listed it, I got my Spark, and Hadoop came in there too. So those two came in together because of a dependency, and the module file system can often handle that for you. And then you can look at what's in Spark, what version in it. You can see it loaded Hadoop for you. And it tells you the path of where it is. So this is the advantage. You can begin to customize these files. Now, if you want to do things with a script, I'm at times kind of lazy, so I make these shell scripts, and then to use them, you have to source them like they're a shell script, like .bash rc. And so all you do is in here I specify my shell, I purge, and I'm going to load CUDA, or I'm going to load Intel. And once I load in, I do a purge, I load in my module files. The only thing I've got is CUDA, and I can find the NVCC compiler. But notice I can't find MPI run because I purged it. But now if I come and I load the Intel environment, I purge everything, I source this script, and I list my modules, and yeah, I've got the default Intel and MVA pitch, and I can find MPI run in the MVA pitch 2 opt directories. That's what I want to use. I don't want PGI, I'm trying to use Intel, and I can't find NVCC any longer. Now I could do for hybrid, I might load, I might be doing MPI GPU, and I would load the CUDA module in there, and then I would have all of them available. So you can customize things, and if you do a lot of complex compiling, then you would see, oh, this could be useful. You might see that as useful. Okay, so sometimes the command is not found, and so you want to source this cleanup script, and often they recommend that you just put it into every script in your bash shells, just clean things up and load the modules that you know you really want, so you're in control. And this becomes clearer when you're working on heterogeneous computing environments, which all HP systems are, because even if they're all the same Dell CPU model or AMD CPU model, they're going to have different versions built every year because hardware dies. And once you have different versions, they're slightly different. It's heterogeneous. So I advise you, take some time to learn to do this. We support a lot of compilers: Intel, Portland PGI, GNU, just GPU, MVA pitch, OpenMPI. And if you can't find what you need, talk to consulting again and see if they can help you figure out what you really need. And if you're having trouble with all of the compiler options that are required, there's people that can help you figure that out. We have MPI, OpenMP, GPU, and hybrid nodes and software. So again, if you're doing MPI, but you need the PGI, and if you're just starting out, the different compilers, Intel, PGI, GNU, they have different performance profiles and characteristics depending on your application. So you might find on Comet, you have one application that's using Amber, and it runs better with the GNU compiler. And you have another application using Gauss, and it might run better with the PGI. So you should, when you get to the point where your code's running and you're profiling the performance, keep that in mind. Not all compilers are the same. So my advice is to consider them. All through the Comet user guide, you'll find these sections that they lay out in a table. Information about the languages supported, or at least these three popular languages. We have Python support as well, and the different parallel programming models over here: MPI, OpenMP, and hybrid. There's a table for GPU. Now, I just discovered in getting ready for this meeting an impact of the CentOS conversion is that this argument to I4, it needs a Q in front of it. But when you try to compile with that command for OpenMP, it gives you a response that says you need to use a -Q OpenMP. So my other notes are updated and will be updating the Comet user guide. And so I have examples for MPI, OpenMP, and hybrid, and some GPU. Okay, so Intel compilers and MVA pitch 2 will be loaded by default. And if you want something different, now you know how to do this with modules. And once again, here's some examples of purging. No modules are there. Load these two, and now you can see that those modules are present. Okay, so let's see. If you want to use advanced vector extensions, those are supported on Comet. And these just give you optimization for certain built-in operations. So some examples on that. And again, for more information, we have the math kernel library, and I will give you an example on how to compile that library. It's not trivial. And if you have trouble and you need to use it again, talk to the consultants. They're there to help you with that. And then below, there is a directory called Share Apps Examples, Phys 244. And this is a physics computational science class taught by Mike Norman. And it has a lot of examples. There's tens of examples in there. And some of my material, I've pulled that out, modified it for the tutorial today. But you can find lots of examples in there. And I'll show you how to do the compiling. Yeah, okay, here we go. So there's a file called compile.txt, and in it, it's got all the commands, all the terms that you need, you're including a lot of libraries. You're going to use MPICC, there's the name of the output, and there's the C file, and then some commands that need, some arguments that need to be included. And so make sure the environment's right. That's what this little box says here. And that way you can compile correctly. And I'll show more examples down when I have hands-on examples of explicitly what the outputs look like. So for PGI, it's the same story as Intel. You'll find a table on the user guide that these command arguments that you need to use for the different programming models. And again, if they don't work, contact consult so they can fix the user guide. GNU compilers are going to be very similar. I have more information on the GPU examples down below. All right, so to run jobs, there's different parallel models, just a little overview for people who are kind of new and saying, oh my gosh, why do I have to do parallel computing? But the model that you use, whether it's distributed or shared memory and other factors, impact the language, Fortran, C, C++, Python, the libraries you use, and the performance. So there's a lot of things that go into the models. If you already have an application that your team is using, then life is simple. That's been chosen for you. So how you choose to run the job, you can run it by command line execution, or you can use the batch queuing system. Some jobs can be run in the command line, but we don't want you to run anything that's parallel and anything that will consume a lot of resources. And so you have to be aware, because when you run something that uses up all the resources, everybody knows you're running something and using all the resources. And you might hear from sysops, and they'll try and help you figure out how to get onto what's called an interactive node, where you own the node and you can do what you need. And I'll talk about that. Comet uses the Slurm, Simple Linux Utility for Resource Manager. And you can have batch queue, and you can have what's called an interactive job. You submit a request to the batch queue, you wait a few minutes, and it finds a node, and you're logged directly onto that node. and then data IO, there's a lot of choices, and we have a webinar on that that was recently presented. And if you really are concerned about your data IO, then go follow one of those webinars. I'll just say that one thing Jeff Sale has been leading an effort for is to take all of our webinars and turn them into what we call interactive videos, where you can scan through the recording of the presentation, see the transcript and search the transcript and be taken to the part of the presentation where something was discussed. So we're working hard to get all of our webinars converted. All right, so there's different models for how you manage your memory. There's distributed memory and shared memory, and it's supported in multiple languages. There's a large number of libraries that are customized to each of these models. And it can, depending on your choice, it can make it a little more complicated. This is an architecture of simple distributed memory. You have a node with one CPU and some memory, another CPU and some memory, but they only way these CPUs can share data is to communicate over an interconnection network. And even if you're on a node where it's got 85 cores or 128 cores, at the end of the day, each of those cores has to be able to share data. That's where GPU architectures are so popular, is they've really optimized that for small problems that need to move data between them, the different cores. So the advantage is you can, for example, imagine these little boxes are each compute nodes with hundreds of cores on them. And the compute nodes can share data. And now you can take a project that maybe doesn't run anymore on one node because it has too much memory, then you can share the data across these different nodes. But at the end of the day, they have to exchange information. So that's the model for the message passing interface. That's where MPI came from. Then there's the shared memory. You'll notice there's still an interconnection network switch, but all of the CPUs, they share this memory. So it's considered physically closer and time-wise closer to the CPU. And if you look at the architecture of a chip, they have levels, different levels of cache. That the closer to the chip, the smaller the amount of data you can store, but the faster it moves in and out. And so when you're computing, you're actually staging data through different levels of memory, and optimizing that is something that can be challenging. And if you're new to this environment, get your code running, and if you can't, get some help. If you're migrating it from serial to parallel. And then when you get to a point where you feel like it should run faster, or you'd like to know about that, Exceed has the Extended Collaboration Services Group, ECSS, and they'll work with you. They're paid to help you optimize your model. So whether you're doing distributed or shared memory, they can help you look for ways to improve the performance of your model, because it's fully recognized within the HPC community that the architecture of these systems are really complicated, and they're not going in the simpler direction. So, okay, so a couple of caveats. Do not run on the login nodes, even for a simple test. Get yourself an interactive node, or submit it to the batch queue. And I'll talk about what's a queuing system in a moment. All the jobs must be run via this Slurm schedule, and you can ask for an interactive job using the srun command, or batch jobs, and I'll show you examples on both. But to do an interactive node, what this means is you'll submit a request to the batch queue, and you may have to wait depending on how busy things are, but once the batch queue can find a node that's available for you, one node, two nodes, whatever you need, then you will get back a prompt that shows that you're on a different node, and that's actually your interactive node. You can run your code on an interactive node. It's a great way to run your Jupyter notebooks, for example, or some visualization code, some MATLAB. And you have to tell the system how long you want it. In this example, I'm using the debug queue because sometimes it's a lot faster. How many cores do I want on that node? And what my shell will be. Batch jobs are, you write a script and you use a command to submit it, and you have to tell it the partition, how much of the node you want, how long the job will run, the number of nodes you need, memory requirements. Let's say you need big memory, 128 gigs, then as opposed to a smaller job, then you need to specify that. Job name, where you want the output to go, and email if you want email sent to you when your job is done. So this is basically the architecture. It's pretty complicated, but one of the big things to get from this is you're over here trying to submit a job, and you submit it. The Slurm is running on this node, for example, and when the Slurm has decided they have enough cores for you to run your job, then your job gets distributed, let's say over these 4 nodes, and your job will start running. You submit the job, and then you wait, and once the job is allocated, you'll get a message back telling you the job is running, and you have to monitor then in the queue, is my job still running, is it done? Unless you write your code to save intermittent data during the computational runtime, like saving it to a file, you won't get any output from your code until the job's all done. Then you get this big output file. So you have to learn to figure out, is it worth my time to try and write a bunch of data during the job or not? But that's a side issue. So what you've got here is when you submit the job to the Slurm using the sbatch command, and I have examples of that, then you're talking to some kind of daemon that goes and looks at parsing the information and what command did you run, and parsing the script for environment variables that tell it what to do to set you up. Is it CPU? Is it GPU? Is it a Fortran code? I mean, and where do you want to store your data? Do you have any input data? And eventually, the job gets submitted and run. So its job is to know what kind of job you want to run and make sure you've defined it. If it isn't properly defined, you just get back an error message and you haven't hurt anything. It will tell you what the problem is, and you fix your batch script and resubmit it. Once it's running, the Slurm scheduler figures out what queue did you pick, when and where will your job start, and terminates the job when done. And you might notice when a job says it's done, as you're monitoring the queue, it can take a long time, like minutes, for the queuing system to finish up the job before you get your output. So be aware of that. Partitions on Comet, we have shared GPU and compute. And so you'll request GPU, or you say, no, I don't need to be charged the full rate. There's like a charge rate for using these different resources. And you might say, no, I can share the node, and you might get in faster because you could back shove a job into a node that's not fully utilized. Or you might say, no, I need to own that whole node because any other activity on that's going to hurt my application. And then we have this MPI environment. It doesn't show the GPU nodes, but MPI run is used to run your jobs. And you always have the idea of this parent node that keeps track of what the other nodes are doing. Again, you can find this table and the current limitations in the Comet user guide. And to specify, and I'll show you examples of batch code, pound sbatch, that is the keyword syntax for the Slurm system to interpret your script. Okay, so common commands. You want to submit a job, sbatch mycodeslurm.sb. The extension, you can call it whatever you want. Some people use .bat. SB Slurm batch means it's a Slurm batch file as opposed to .cu, which would be CUDA. You can call it what you want. We tend to use that in our training. And once you submit it, if it reads the system will read your script, and if it's all good, making sense, then the job will get submitted. Otherwise, you'll get a rejection error message, and you can fix your script. And so you'll get a job number, and you can monitor the job to see if it's running and what its state is using the SQ-U user. Your user ID goes here. And you keep looking at that manually, and all of a sudden it's done, and you'll see your output file when it does finish. Here it's pending, and the job is now running. Okay, so it's about the right time. I'll try and go through. I put the GPU first because that's the most, it's probably newest and complicated. And I'll focus on the MPI probably since we're getting late in time. But they're all the same pattern. It's mainly for you to recognize the pattern. Again, you want to just make sure that you've got the executable and you're going to submit this job. Now, in the MPI example, there's two subdirectories. One is called IB run, and the other one is called MPI run _R shell. And these are just two different ways to run your code. This one is using the Intel IB run command. So let's compile and run the GPU CUDA. So we have Kepler's and Pascal's. When you run jobs, you actually have to have a separate allocation for the GPU. So even though you may have a Comet CPU allocation, you need to apply for GPU allocations to be able to run jobs on them. So if you have questions about that, get in touch with, look at the Exceed user guide or talk to a consultant. So we want to make sure that we're on a node that has a GPU card. And this is little commands that you can use to recognize and figure out what's on your node. This node here, the login node, doesn't have any GPU cards. But if you get a node that does have GPU cards, then you'll get some information. So it's a little handy command. So in the CUDA directory, Comet 101 CUDA, there's just most of these belong to the matrix multiply, and I've reorganized the directory. But basically, I've just got a hello world example for you guys in there. You want to make sure that you've got your NVIDIA. I need to load that CUDA, or you can't compile. This is the simple command for compiling GPU enum. GPU enum is a code that will run some commands and look at the device and return device information for you. How many blocks, how many threads. And it's good to start writing your code where the first thing you do is run these commands that give you profiles of your GPU card and then distribute your work based on that GPU card, because again, they're not all the same. And so recognizing and learning about that's important. So I'm gonna, this one is an example of running an interactive node. Module load CUDA, make sure I've got that. The srun command, here I'm gonna go to GPU shared. How many tasks I want is 7. I'm gonna use it for 10 minutes. I'm always trying to, mine are short, just for examples. And then this one took 35 minutes to get, but finally I ended up on a new node. Comet 3309, and that's the host name for the node that I'm on. And I can start doing my GPU. So I'm on this node and I'm gonna run a command called NVIDIA-SMI, which will tell me about the hardware on that node. And so to run GPU through the batch script, and you can run Jupyter notebooks that run on the GPU, by the way. So you can run Jupyter notebooks on CPU and GPU nodes. For GPU CUDA, the batch script configuration, you can define the partition to be GPU or GPU shared. GPU shared, other jobs might be on that same node. But you might get that faster and you might be charged fewer CPUs for that. You also need to specify the type, and on Comet there are 2 kinds. And this little table down here tells you if I use GPU:4, that says give me the first available one, I don't care. And you can be sure on expands when we have V100s, people will care. They want their code on the faster nodes. Or if you want P100 or the K80s. If it depends on your needs, but you can specify which flavor of GPU you want. Here's an example of a batch script. It worked for me. Hopefully it works for you. I give it a job name. I tend to give the job name the same as my application, but that's not always required. There's no formula. You can call it foobar if you want. And then you give it an output name, which will give you this %J is the job ID, this %N is the node name. And so you'll get a name that's a combination of the application, the job ID, and the node name. What partition I want one node. I'm going to run 6 tasks. And I've commented out this sbatch command, and I'm going to ask for 2 nodes here. And I'm going to load the module. If I was going to do it really cleanly, I'd put in module purge and also maybe that cleanup script, and then I'll run the job. And so I submit it, I get a job ID. I'm monitoring my jobs that I've submitted. I have a couple things going. Looks like I have an interactive node and I've submitted my GPU enum. Finally, it gets done, and here's my output. This is for an example of just asking for 1 device. And you can add, in my markdown, in the online markdown file, I show you how to get multiple devices. Okay, running MPI jobs. I'll try and go quickly through this. I see we're running a little bit late. So in the MPI directory, there's the Fortran code. Here's your Fortran code, basically hello world. I always give hello world because if you set up hello world and it works and things don't work on your new code, you can go back to hello world, run it, and if it runs, then you know certain parts of your user environment are good. So hello world's helpful to have. So I'm going to do the standard purge, load the intel, make sure I've got the right commands, run my compilation. This was pretty simple compared to the math kernel library example. I'm running this, I'm typing out my host name. So I'm going to go down into into the IB run directory, which is an example for running I don't need to be in the IB run directory for this. That looks like a typo to me. I'm trying to get an interactive node here. And so I'm waiting for my interactive node, and when I do get it, I look at the host name, it's different, and I can run my hello MPI on the command line, and it works fine. So I'm going to exit that interactive node. So exit the section when your work is done, or you will be charged all the CPU time. And try not to oversubscribe your job asking for more cores than you have. It's allowed, but your performance will be affected. Now I want to be in the IB run, and I want to look at my job submission script, which is going to run hello world, hello MPI, and I'm going to submit hello MPI slurm. Notice it's got to find the executable, which is in the directory up above. Okay, and so I'm waiting for my job to finish. Finally, it does finish, and I get my output file. So I submit my job, I get a job ID. If you're doing a lot of testing and debugging, start writing down those job IDs. It's really easy to lose track of them. And here's the output from this. There's a whole lot of information I don't need, but there's my data. Hello and welcome. And it looks like I've got different nodes, and I've got about 12 of them, about 10. Okay, so the pattern for the rest of these is the same. Running OpenMP, load in this is an OpenMP with the pragma directives. Make sure you've got the right modules in, compile. Notice I'm using the -q OpenMP, and you can run OpenMP from the command line. You just might not get very good performance. And you need to also sometimes control the thread behavior, like you want a particular number, and so you could export the number like 16 threads, or some hardware will scale to multiple threads per core. So if you have a 32 or 24 core node, you could probably safely scale it to 48 threads. I wouldn't go much more. And so playing with threads is interesting, but you have to be aware that it's possible to submit a job and have all the threads launch on one core and all the other cores are sitting there idle. and that's called binding, binding. I don't show an example, but you want to study the binding, and then you can tell the system 1 thread per core, that's it. And that way you get that core performance. Okay, and so got a bash script and some output. Submit the job monitor, again, the same kind of partition. Hybrid MPI is actually pretty much the same. We use a wrapper and MPI and OpenMP, MPI GPU. What you need to do is to make sure you're including the right libraries. You still have to initialize MPI, bring in your OpenMP environment and commands, and let your code run. The command, you have to add in the OpenMP argument, and everything else looks the same. The SBatch doesn't change. The batch script doesn't change. But we do have to, we want to define the number of threads and then the number of threads per node. So because we're doing OpenMP, we do worry about the distribution of the nodes, of the threads on the different cores and nodes. And so submit the job, it finally runs, and there's the output. So I modified this to show you that which thread, all right, and which core are these all running on. So we're getting multiple threads running on multiple cores, basically. Okay, and that's pretty much it. Running jobs can be really complicated. I went through this very quickly, but there's a lot of little pieces, and debugging is the hardest part, and knowing which part of your system is working or not. So unit testing, it works really well for HPC. You have Hello World, and make sure as you're building up an application that you build up some test cases that when things are right, they always work. And when they don't work, it's not you, perhaps. Like if Hello World in MPI doesn't work and it always works normally, then it's probably not you. And you can save yourself tens of hours of debugging, especially as your applications get more complex. It can take a long time to debug all the components from the software stack to the hardware stack and back around. So build up those test cases. Use a GitHub repository. When things go wrong, you can get back to your working version. And if you need help, contact the Exceed desk. Check your user environment. Final word. Do you have the right modules? And sometimes you have to log out and come back in. We did discover last summer sometimes that you come onto a node and it just doesn't load right. So you have to have ways to check that the modules in your environment is the one you really need for your application. What software versions do you need and what are you using? Sorry about that. Is your code compiled and updated? This is a big caveat today because we have a new operating system and a lot of people are still struggling with it. And it's a lot of little tiny changes. So be aware that is your code or are any of your libraries updated and which version are you using? Are you running your job from the right location? Luster Scratch, use Oasis Scratch Comet user. You have a labeled temp project in this file, this NFS mounted disk space, and use it. Just remember it's not backed up, so move your data somewhere, like to the Luster long-term file storage when you're done. And it's really good for large block I/O. Compute GPU nodes, they have local storage. And again, move your data off if you need to. And then there's the Luster projects file system. And this is for students. And then again, finally, the user guide, training resources for SDSC and for Exceed as well. And with that, that's it.
Thank you very much, Mary. That was excellent. The only question on the chat was in regards to how long it might take for a password change to take effect. I speculated it should only be a matter of minutes, but I wanted to check with you.
If you do it from the command line, I don't know if
I-
you can. I think you have to go online. I
That's
don't
right.
know the answer to that. If you're doing it online, it should be pretty quick, but if you're having trouble, again, just contact consultant, they'll fix it pretty quickly. I really can't, it depends on the system you're on, but on Comet, I believe we have a form and it's pretty fast, but I'm not gonna guarantee that. So I would ask them.
Yeah, that's my understanding
Yeah.
too. And there was
I'll
another
make a
question
note.
about why do we sometimes get LN1, LN3, or LN2 when we log in, and I explained that our login node, we have multiple login nodes, but they are identical. There's no difference.
They are random. Yeah. They're identical. They see everything the same. They're just load balancing the servers. But it's possible you can log in directly to a node. If you get the node allocated to you, you can log into it directly. In other words, you're a valid user on that node. So if you wanted to always log into the login node 1 or 2 or 3, you could try to log into it directly. But they're identical. And so just trust that the system knows what it's doing.
Yeah, we will be making a recording and the slides available soon afterwards. Zoom transcribes this recording, but they are being pounded thanks to the virus. So it might take a day or two.
Good.
Any other questions? Okay, well, I'll follow up with a couple of folks who had some very specific questions offline. And thanks very much, everyone, for joining. Thank you, Mary. Have a great day, everyone.
Okay, guys, thank you so much. Stay safe and thanks for coming. Maybe we'll see you next month. Bye.